In this video, I will be performing a direct transient response analysis using solid elements and cylindrical coordinates. Full details of this exercise are on page 410 of the PDF linked in the video description below. I'll first start a new Patran session. The units for this exercise are in inches, pounds, and psi. I'll be defining a new cylindrical coordinate system after I create my Patran file called prob19. Click OK here and I'll jump to the geometry tab to create my coordinate system. Here we're using cylindrical. The origin will be 0, 0, 0. The point on the axis 3 will be 0, 1, 0, and then the point on the 1, 3 plane will be 1, 0, 0. Here's my new coordinate system. I'll create a surface using the XYZ method. From point 6, 0, 0, I'll make a surface that goes 6 inches in the X, 8 inches in the Y, and 0 in the Z. So hit enter or apply. Here's my new surface. I'll then go ahead and mesh this. So I'll go to the meshing tab, create a uniform seed. I'll be giving a requirement of 8 elements for these two edges here. And note that I've selected the edge icon here, so it allows me to select the edges of the surface. For the top and bottom surface or edges, I give it a requirement of 6 elements, and I simply drag and select. And since I have auto execute on, it'll automatically give it the mesh seed. I can then use the surface mesher here. Select this surface here. Make sure the cursor is here. Surface 1 has been selected. Hit apply. Now it's been meshed. Now to make this 3-dimensional, we want to go ahead and sweep it about the Y. So here under Fem Actions, I can select sweep. When we rotate this about the Y, we want it to create 3 elements. We want it to use this coordinate system 0 here, the XYZ one. We want it to rotate about the Y. Right now, coordinate system 0, 3 means that this will be rotated like that. And we don't want the elements to rotate or be swept like that. We want them to be rotated about the Y. So here I can simply delete the 3 and add a 2. Alternatively, I have these icons here, so I can simply select the frame direction 3, 2, or 1. And it will automatically change it to 3, 2, or 1, whichever one I have selected here. But here I know I want 2. So after I select the frame direction 2 and select this coordinate system, I get 0.2. My sweep angle is 30 degrees. I do want the quad 4 elements to be deleted after I sweep this. My base entity list will be all of these elements. So I can simply hit pick all. And after I click apply, you'll notice my new mesh here. So now I can continue with the example. Or actually before that, I have to make sure that all the nodes are in the right coordinate system. So right now, if I do a quick examination of the finite elements, so I go to action, show, node, location. If I pick a few nodes right now, this one, and that one. My reference and analysis coordinate system are the rectangular one. I actually want to use the cylindrical coordinate system here. So what I have to do is go to action, modify. I want to modify my nodes and I want to edit as a method. Check analysis and reference. Simply drop your cursor in here and simply select this coordinate system. We want this to apply to every node, so simply pick all. So all 252 nodes, hit apply. Now we had the feedback a moment ago that 252 nodes have been modified. So we can continue now. So under properties, I can define my material, call this one matte. Under input properties, give it a Young's modulus of 30e, 6 psi, and a Patran ratio of 0. My density is 0.000072499. Click OK and apply. Here under 3D properties, select solid, call this prop. Under input properties, I want to use this solid or this material, and I wish to apply it to all these elements. So here I'll select the solid element so that if I have a wedge or hex elements, I'll select it no matter what it is. So here I'll pick all, or you can individually pick the ones you want. Click add, OK, and apply. So now the material has been applied to these finite elements. I can now move on to my load and BCs. I'll first create a field. So here under LBC fields, click on non-spatial. Here we'll just call it a load or load history. Our load history is time dependent, so make sure that's checked. Under input data, what we want to do here is model this load history here. So at 0, it's 0. At 3, it's 0. At 4 seconds, it actually goes up by 1, and up to 10, it's 1. So here, that's what I'll be entering. So at 0, at 3e to the negative 6, and this is 3e to negative 6. That's 3 microseconds. The next one will be 4 microseconds, and these are actually in seconds. We know at 0 it's just plain 0. We know at the next one it's 0. We know at 4 it's 1, and we know it's 1 at the end. Click OK, and here you'll notice that the apply button's not there. If I move this around here somewhere, if I play with it, you should be able to see the apply button. If not, what you can do is just put the cursor in here and hit enter. And you'll notice that here the feedback is the load history has been created. One thing I have to do is create a new load case or modify my current load case so it's time dependent. Right now my default load case, like in every example I've done, the type is static. We have to make this time dependent. So instead of creating a new one and switching it to time dependent, I'll just modify this one. So here, select modify, select this default subcase, you can minimize this. And we'll make this current. Let's switch this to time dependent and click apply. So now I can define my loads that are time dependent. So let me first go ahead and define my pressure, since it's time dependent, and I'll use the load history we just created. Click pressure here, call this pressure. For our target element type, these are 3D, so just leave it 3D here. Under input data, type in 10 psi. Under load history, simply click this field we created a few moments ago. Click OK for your application region. We'll be applying this to the FEM. And here, what you can do is go one by one and select the various faces. And we're only selecting these ones, by the way. And that might get it a little bit too tedious. There are a few ways you can do this, and I'll show you how to do that. May not be obvious at first. So one way is like this. Let me turn on the shading. So you can see we have a direct view of this here. And this is the left side view. What I can do is select visible entities only. You'll get a message here, you can read it on your own. So then all I have to do is drag a window and select these faces and add. And now the convenience of this is that when I do this, it does not select anything on the back. So you see it's still on. If I have this off and I did the same thing again, it would select the faces on the back too and everything in between, and we don't want that. So just to demonstrate that again, turn this on, you'll get a message. Drag and select, and it's selected these internal ones. Another way is if you go to auto select, and this tool is convenient for when you have various faces that are really odd. Here I can select, or just to demo something real quick, I can select this face here, overwrite, and it'll select everything here based on the defaults. Can add it here and do the same for the next one. Overwrite, cancel, add, auto select again, select this one, overwrite, cancel, and add. So now I've done the same operation. It's tedious here, but you can use this for when you have models with very difficult faces to select. Now that I've selected those, I can click OK and click apply to apply your pressure. Now I can define my boundary or my displacement constraints. So the first one, I will call it hoop symmetry. Under input data, you want to restrain motion in the hoop direction. So here 1 is left blank, 2 has a 0, and 3 has a blank. And one thing I forgot to do there is use the cylindrical coordinate system. So make sure this is chord 1. Click OK. For your application region, we want to apply this to the nodes here and here. And so what we could do here is go back to the left side view automatically, or drag a window and select these nodes, add it, rotate this so you get a nice view of these nodes. You'll notice I did not select this one. Let me add it again. And the reason is because I still have visible entities only on. So it's only selected the ones that were immediately visible to me. Let me turn that off and redo this. So now you see it's selected these nodes, add it, rotate this a little bit more, select these nodes, add it, and now you see have both sides selected. Now you can see if I zoom up, the hoop direction is constrained, and you'll know that I'm using coordinate system 1, which is this one. Let me actually turn on the model tree so I can turn off these boundary conditions. Now I have to define my axial condition here. So let's make a new one called axial symmetry under input data. We'll restrain motion in the third direction. We'll use the cylindrical coordinate system 1. For my application region, we want to select these top nodes, add it, and these bottom nodes, add it, OK, and apply. So now we have that. Now we can go ahead and run our analysis. Move over to this tab, click entire model. Under solution type, let's select transient response using the direct formulation, click OK. Let's modify this default subcase by going to subcases, selecting this default subcase, and select subcase parameters. Here we'll define our time steps. We want 750 steps, and our delta t's are 1e to -6. So that's 1 microsecond. Click OK here, click OK here, click apply here. Cancel and click apply to submit this for analysis. Once this is done, I'll go ahead and hide my model tree. I'll import my results here. I'll go to the results tab, and I'll first make a graph using this tool here. Here I'll click this icon here to display all the results. So select this first result, scroll all the way down, hold the shift key and select this last result. One thing I want to watch are my translational displacements. And I want to view this for a few select nodes, so pick any 3 nodes basically. So I'll select this one, the one in the middle here, and this last one. So once that's good to go, I'll hit apply. Let me select the X component actually. You'll notice that the results are not the way they are supposed to be. So let me quickly review the model, turn on the model tree. I suspect it's pressure. That is actually correct. Let me inspect the load case, modify this. That is correct. Maybe the field is not correct. That is correct. Now I'm wondering what may be wrong with this. If I go back to the results, that is correct. Scroll down this and look at this a little bit further. Under solution type, I have transient response. That is correct. Under subcases, this may not be correct. So when e to the -6. Hit enter, click OK, OK here, click apply here. Yes, cancel, and resubmit this. Here it seems the increments were too small or too big. Let me import the results. Let me look at the graph again. I'm going to view my displacements, my radial displacements, and that would be the X component for the same nodes. I should obtain the same, or the right plot. And that is actually what I do get. Here, let me select tile viewports. Now it's disappeared. Let me hide the model tree. I've actually occurred an error here. Let me delete this plot. It's actually not there now. Let me save this actually and close out of it. Let me go ahead and open Patran again. Let me open that model again. This is problem 19. And it's actually crashed. Now that's fine, I'll just have to recreate this. So I'll start a new Patran session, or Patran file here. I'll call this one problem 19 new. And right now I have an empty session. What I can do is somewhat recover the data. So here under source, go to Nastran input file, input your .bdf file. Now that's in here. Under analysis, click XDB. Under select result file, you'll find problem 19 XDB is still there. Click OK and apply. So now when I go to results, all my results are still here. Let me do a graph. And now I can view the translational displacements for radial components. And let me select those 3 nodes again, so it could be any one of them. This one, the one in the middle, the outer one. Let me click apply. And here's that plot. And let me tile the viewports, and now you can see that. And the problem asks us to do one last thing. And that is view the radial displacements for nodes 1 through 7. So I'm assuming that would be along the edge there, but that would be for static displacement. So I'm wondering if that's available to us, and most likely not. Yeah, in the problem they would let me read this real quick. Here, for a single degree of freedom system, an instantaneously applied load will give a maximum displacement that is twice the static displacement at the same applied loading. So when I look at this is actually for the static displacement. And I won't take the time to go ahead and do that one here. Make sure to save your model. And this concludes this example.